Newton's second law of motion says the sum of the external forces acting on a system is equal to the product of the mass of the system times the acceleration of that system. It's symbolized as sigma F equals ma. Sometimes you may also see it written as F net equals ma, and these both mean the same thing. Newton's second law can apply to any choice of system, and this is one of the things that makes it so useful. It always holds true no matter what. Once you've chosen a system, you'll want to be sure that you're using the net force on that chosen system. You'll want to use the mass of that chosen system and the acceleration of that particular system. For each problem below, designate a system to analyze by drawing a dashed boundary. Draw a force diagram showing all forces acting on that system. Okay, so I'm going to let my system be the 5 kilogram hanging mass. Relevant forces would be a force of gravity and a tension force. To find the force of gravity, I'll use the formula m times g. So this is 5 kilograms times 9.8 newtons per kilogram. And we see that Fg is 49 newtons. Now I'd like to solve for Ft. So I'm going to find the net force in the y direction. It's going to be the sum of Ft and Fg. I put the y subscript on there so I remember to keep track of the signs in the problem. Now, according to Newton's first law, in order for there to be equilibrium, in order for an object to have an acceleration of 0, we have to have balanced forces. So the sum of the forces in the y direction has to equal 0. So we'll have this. I'm going to make the FGY negative because it points down. And now I solve for FTY. It was 49 newtons. What if that 5 kilogram mass, though, is held by 2 strands? It's still going to have the same weight of 49 newtons. But this time, it's suspended by 2 strands, and I'll call that Ft. If we were setting up the problem in this case, we would get 0 equals 2 Ft minus 49 newtons. Add to the other side, and then divide by 2. The tension has now dropped to 24.5 newtons, and that should make sense because more cables are supplying a tension. They each don't have to pull quite as hard. Their efforts will be combined. But what about this problem? Here we'll see how the designation of system really can help us solve problems that otherwise would be impossible to solve. The first thing I'll do is I'm going to find the tension in the lower cable by just analyzing the 4 kilogram object. The 4 kilogram object will have a weight equal to 4 times 9.8. Kilograms cancel and we'll be left with 39.2 newtons. Okay, we have the weight of it. Now let's show how it's being held up. It's being suspended by a tension force, which I'll call T2, because I want the upper tension to be T1. We can clearly see by the symmetry of the situation here that T2 has to be 39.2 newtons. Now, how do we find the tension in the upper cable? For that, we need a new choice of system. I'm going to now let everything that's hanging be the system. In the free body diagram, we'll have a weight and a tension force. T1, and I'll call this the weight. Now the weight is going to be 11 kilograms times G. The weight is 108 newtons. So this tells us that that upper tension has to be 108 newtons. By making two different choices of system to analyze, we were able to find two different cable tensions.